So I decided to call this a useful fact, for lack of a better word. So let's let f of x be an even function such that its Cauchy principal value exists. So then in that case, when f is even, special case, the improper integral from minus infinity to infinity of f of x dx does converge and is equal to its Cauchy principal value. And so that is really great to know. Something special happens for even functions. I'm not going to justify it, but I would encourage you to open your book. I forget the page actually. It's just at the beginning of chapter 7. I think it's on page, it looks like maybe 262, somewhere in there, 263. That you can read about, what happens, or play around with it yourself. You probably can see yourself when f is even what happens. So also, one other thing, when f is even, then you actually get something else out. You know that the integral from 0 to infinity is, 0 to infinity of f of x dx. Well, this is just 1/2 the integral from minus infinity to infinity of f of x dx. And of course, this is equal to the Cauchy principal value. Maybe we should put it like this. Equals 1/2 the Cauchy principal value of the integral from minus infinity to infinity of f of x dx. So if you get lucky enough to integrate an even function, then you know that the Cauchy principal value is in fact the same as the integral, the improper integral itself. And so we're going to look at some rational functions of complex numbers, and we're going to use those to come back and work out integrals of real valued functions. And so let me show you a little bit of the setup here. So we're going to start with a real valued rational function. Here we go. Okay? And I want to assume that p and q share no common factors. You've simplified everything. And I want to assume that q of x actually has no real zeros. Okay? But q has at least one complex zero above the x-axis. So it has no real zeros, but when I think about it as a complex function now, it does have at least one complex zero above the x-axis. And so I'm going to imagine that these are all the zeros of q. Here they are, z1, z, I said a z2, really I should have made that one z2, whatever, z2, out to zn. So you've got a scattering of zeros. Maybe there's other zeros of q down here, but I only care about the ones that are on the positive, that are above the x-axis, and I am assuming, right, that q has no zeros on the x-axis itself. That's really important. And so we're going to look at this particular half circle. We'll call it C, and I'm going to think about it in two parts. You have the x-axis part, and I'm going to go from 0 out to r, 0 out to minus r, and then I've got this half circle part of radius r, which I'll call gamma r. Of course, we're going to have positive orientation like that. Okay, well, if you think about it, then all of a sudden, if you want to integrate f of z I'm thinking about as p of z over q of z, the integral of c over the integral of f of z over c. Well, let's jump right to the gun over here. Using all the theory that we've just talked about, using Cauchy's residue theorem, you know this is just 2 pi I times the sum of the residues of f inside of there. On the other hand, you can break this up into two parts. You can break it up into the integral over this curve right here, plus the integral over this curve right there. And this part in particular, technically it's f of z dz, but we're on the x-axis, so the z's are all just real numbers, and so you can switch this to f of x dx. And so interestingly enough, we can compute both of these. Okay, the sum here we can compute as the sum of the residues of f that are inside our circle. And this part, as r goes to infinity, is going to go to what we want. We're interested in the integral from minus infinity to infinity of f of x dx. So this is going to converge to what we want. We've got the value over here, the only thing that's in our way is this. And so what do? We either need to be able to compute it or get rid of it somehow. But if we can show that the thing that I was just boxing, if we can show that the limit as r goes to infinity of this integral, the integral over the circle gamma r of f of z dz, if we can show that this integral, that the limit as r goes to infinity of this integral is in fact 0, then you know that the principal value of the integral from minus infinity to infinity of f of x dx is just the part that's left. It's just the sum of the residues. It's just 2 pi I times the sum k equals 1 to n of the residue z equals zk for f. And again, I'm not saying every residue. I'm saying you only have to worry about the places, the zeros of the denominator that occur above the x-axis. Now you could draw a similar picture with your curve C going below the x-axis and play the same game. I certainly don't want to pretend like that's not the case. So that's the idea. So in the next video, maybe I'll have to do two. We'll see. I want to work out an example with you and show you how this works.